All right, we will now solve Laplace's equation on the unit disk. So we're now in 2 dimensions, much more exciting. And what we know about Laplace's equation is that it comes with boundary conditions. So the values on the boundary are prescribed. So the physical problem that you might imagine is the equilibrium heat distribution in the circular room, given that you know what the temperature is at the walls. So that's the problem that we're going to solve. And Laplacian equals 0, I've already ranted about. What did I rant about? That Laplacian is too important of a concept to define it as the sum of second derivatives, because this is in Cartesian coordinates. And what made Cartesian coordinates king? No, there's just no reason. Especially now. Now Cartesian coordinates make absolutely no sense, because our geometry does not align itself with Cartesian coordinates. If we have any hope of solving this equation in a reasonable amount of time, actually I know a way to do it in Cartesian coordinates, so it's possible, but so to do it in the most convenient fashion, we will switch to polar coordinates. And as you can see, the boundary condition is given, it's not really polar coordinates, it's just that I imagined a parameter on the perimeter of the unit disk, on the unit circle, and I called it alpha. It's 0 here, pi, 2 pi. It goes from 1 here to -1 here, back to 1 here, back to -1 here, back to 1 here. So it goes up and down, up and down. So that's the initial condition. It's almost like there's a heater here, a heater there, a window there, and a window there. So what's the temperature distribution everywhere else in the room? And of course, we're going to go to polar coordinates. So the exercise that we're going to go through right now is converting the Laplacian to polar coordinates. All right, we will now begin solving Laplace's equation expressed in polar coordinates on the unit disk. And of course, these are natural coordinates for the unit disk, because in polar coordinates, the unit disk is described by the equation r equals 1. Whereas in Cartesian coordinates, it's described by the equation x squared plus y squared equals 0. Or x equals r cosine alpha, y equals r sine alpha. Much more complicated. But I don't even have to say anything for you to agree with me that the polar coordinates are natural for the unit disk. So we'll now have to find a function of 2 variables, r and theta, that satisfy a function that satisfies this differential condition in the interior of the disk, and some given boundary condition, for example, cosine 2 theta, on the boundary of the disk. So we're going to use the same technique that we used before to separate time from space in the context of the heat equation and the wave equation. And the reason why it was possible, and that reason is still present here, is because there was sufficient symmetry in the problem. In fact, time and space were kind of separate in essence to begin with. Well, here we will be able, because this shape is so beautifully symmetric, we will be able to separate r from theta. We will be able to represent the function of r and theta as a product of 2 functions. One, a function strictly of r, and another, a function strictly of theta. And of course, what we will discover is that there is not one, but infinitely many functions like that, which will be great because we're still dealing with a linear equation. So we will be able to put those infinitely many functions that we discover into linear combinations, and thus form a solution to this boundary value problem. We will adjust the coefficients for those functions so that the resulting function matches the boundary condition. So that's what we're going to do. So we're looking for a solution of the form. So capital R and capital theta are the names of those functions. So I want you to think of this as two parts. This is a differential operator that only differentiates with respect to r. And this is a differential operator that only differentiates with respect to theta. So when we plug this into this combined operator, this part will act only on r, and this part will act only on theta. The other multiple surviving unchanged. So when we plug this into the Laplacian, here's what we'll get. So I will drop the argument. When you see r, it's a function of little r. And when you see capital theta, it's a function of little theta. And because they're ordinary functions of one parameter, I can write the ordinary derivative. So we'll end up with ordinary differential equations. And then, as always, to go towards separation, I will divide the entire identity by r theta, which will cancel this theta in the first term and this r in the second term. Okay, a step in the right direction. But as you can see, the variables haven't quite separated. Because while this term depends only on r, this term depends on both r and theta, because this is a function of little theta. So we've got to get rid of r squared here, which I will do right in place by multiplying both sides of this identity by r squared. Now we have two terms where the first term depends only on r, and the second term depends only on theta. So instead of adding them up and making them equal 0, I will say that one has to be minus the other. Okay. Now we're able to say what we said before. If on the left we have a function only of r, and on the right we have a function only of theta, then both must be constants. And so both must be constants. And now let's think for a moment. Will it be a positive constant or a negative constant? What are we going to end up for the equation for theta? Whatever this constant is, the equation that we'll end up with, don't forget this minus. It's that theta, the second derivative of theta, equals that number, whatever that constant is, minus that number times theta. And theta is the function that captures the angular portion of u. It needs to be something that's periodic. It needs to be something periodic. So not exponentials, but sines and cosines. So we want it to become such an ODE, so its solutions are sines and cosines. So this, because of this minus sign, needs to be a positive constant. N squared will denote it. Very craftily, n squared, as if we know what's coming next. And so now we have two ODEs. Instead of having one complicated PDE on a two-dimensional domain, we now have two ODEs. And the angular ODE with which we'll start reads, maybe I'll do it here. Again, we'll have to say, what is that constant? The letter that I chose kind of suggests that it'll be an integer. But does it have to be an integer? Could it be 1.5? Well, let's see. Let's start thinking about initial conditions or boundary conditions. Let's start making sense of what we've got. Whatever this function is, we're looking for smooth solutions here. And so as you go from 0 to 2 pi, if you want to think of the rip as being here, or if you want to think of the rip as being here, from minus pi to pi. And it has to come back right back to where it was. So n does need to be an integer, because the solutions to this equation, the solutions to this equation are sines and cosines of n theta. And if we want continuity, then n has to be an integer. And so the letter n is an appropriate choice. So that's sort of the quantization. Even though we don't have an well, we do have an eigenvalue. This is an eigenvalue problem. And that's the quantization imposed by periodicity. And so the solution here is beautiful. I'm kind of going through this quickly because we've seen this before. And this guarantees periodicity, not just of the function itself, but its derivative and so forth. Okay, so that's nice. We're solving Laplace's equation. And we can even start putting together what the solution will look like, even before we solve this ODE. The solution will look like this, ultimately. Remember, because the equation is linear, will be a summation of all of these possible things that we'll find, of something that will come from solving this right here. So we'll save space for it, for the radial part, times a, now it has to be a sub n, because it's summation over all of these, from 1 to infinity, and I should even write from 0 to infinity, because we should be allowed a constant term here as well. N can be 0, and it still makes sense. And with the caveat that there is no such thing as b sub 0, but this should really be 0. And so we can anticipate how we're going to match boundary conditions. When we plug in r equals 1 here, in other terms, we're plugging in r equals 1 here. I'm not quite sure yet what will go here. But we'll end up with some kind of a Fourier series. So part of the recipe will be to take a look at the boundary condition, a beautifully periodic function, decompose it into a Fourier series of some kind. If we're lucky, these will be the actual Fourier series coefficients. And then put the solution together by multiplying the angular part by the appropriate radial part. So let's figure out what the radial part is by solving this equation, which of course becomes... Okay, let's talk about this equation. When you look at an equation, what's the first question you ask yourself? Is this equation linear? Yes, absolutely it is. Is it linear with constant coefficients? No, they're not constant coefficients because the unknown variable, the independent variable appears as a multiplier in these two terms. So what we lose when it's not a linear equation with constant coefficients, what we lose is the fact that our solutions are simple exponentials or complex exponentials. That's what we lose. So we'll have to find another form here. And here it happens to be somewhat simple. In fact, I'll tell you what it is. It will be r to the n and r to the minus n. Why don't you take a moment, plug it in, and make sure that it works. Let's do it together. Let's take r to the n, and then we'll save that one for doing it at home. So this will, when you plug it into here, taking two derivatives, we'll introduce a multiple of n times n plus 1, n minus 1. And then the power will drop by 2, but then r squared will restore it to its original power of r to the n. So it'll be this times r to the n. What happens here? You pick up a multiple of n. The power drops by 1 to n minus 1, but then this r restores it to r to the n. So it's plus this much r to the n. Finally, minus n squared, and each one of these is multiplied by r to the n. And is the expression in parentheses 0? Yes, it is. So r to the n works. And similarly, r to the minus n will work. But because we're solving this equation on the unit disk with nothing special at the origin, we have to reject these solutions. And we're only left with r to the n. Otherwise, it would have been any multiple of this plus any multiple of this. Once again, linear equation. If this fits and this fits, then any linear combination fits as well, satisfies. And this all is consistent with our paradigm of solving ordinary differential equations. Or in this case, you may think of it as a partial differential equation with just one variable. They always come with corresponding boundary conditions. And this equation we would be solving from 0 to 1. And so you need two conditions. And one of those conditions is being finite at the origin. This whole business with infinities, which occurred because of this and because of this. Do you see this operator seems to blow up at 0? It's not because the origin is any kind of special point. It's just that the coordinate system that we're working with has a special point at the origin. It's a singularity. For points at the origin, r equals 0 and theta is anything you want. So there's something funny going on at the origin. Lack of uniqueness. As a result, derivatives go to infinity or multipliers go to infinity and so forth. It's just a special property. It's just a kink introduced by the coordinate system, not by the problem itself. And so the corresponding initial condition, if you want to think of it that way, I think of it as a boundary condition at 0, is that at least the value is not infinite. So that makes d sub n equals 0. And so the whole term goes away, and we're only left with this. And so we don't really need this c sub n, because a sub n and b sub n give us sufficient freedom. So all we have here is r to the n. And then what we have left is basically, because all of these end up being equal 1, we just have a Fourier series. So all we need to do is decompose whatever the boundary condition is, and I chose an overly simplistic one for a reason, because it's the overly simplistic that sometimes trips students and adults and professionals. Okay, so that's what we need to do. We need to decompose the boundary condition in a Fourier series, and then every nth term gets multiplied by r to the n, gets a radial part tacked onto it, and then you add them all together. And the insight that this provides, even before we determine the coefficients, is fantastic. It just says that whatever frequency you observe on the boundary, it decays towards the middle at a rate proportional, so to speak, in terms of exponent, to the frequency. So the average doesn't decay at all. A smooth one swing variation decays linearly. A double variation decays quadratically, and so forth. And that's why by measuring, let's say, temperature or currents or potentials, as long as the field satisfies Laplace's equation, in the middle, we can reconstruct some things about what's going on the boundary, but not others. So low frequency information we can reconstruct pretty well. High frequency information has decayed by the time it got to us. So a very common issue in what's called inverse problems. Okay, so now we can actually dot the I. And all we need to do, there's actually not much to write other than the solution, is to decompose this laughable boundary condition as a Fourier series. And what you need to realize, it's sort of Fourier series 100, is that it's already in the Fourier series form. It's like somebody gave you a polynomial and asked you for the Taylor expansion of that polynomial. It's already in that form. It's like somebody gave you an orthogonal matrix and asked you to perform QR. It's already in that form. R equals identity. And the matrix itself is Q. So it's one of those. You don't need to evaluate these integrals or whatever equivalents we had for real numbers. It's already in that form. You can still do it, but of course you'll get the answer that all coefficients equal 0 except A2, which equals 1. The Fourier series is A2 equals 1, and all the rest are 0. So instead of an infinite sum, we have a single term, and that single term is, of course, r squared cosine 2 theta. So that's the answer in polar form. And just for fun, no good reason at all, let's write the solution in Cartesian coordinates. So as a function of x and y. Does anybody see how to easily translate this into Cartesian coordinates? One way to do it is to write that r squared is x squared plus y squared, and to write that theta is arctan of y over x. And then somehow evaluate cosine of 2 times arctan of y over x. So that, of course, is a silly way to do it. A much better way to do it is to remember the double angle formula, I think it's called. Cosine of 2 theta is cosine squared theta minus sine squared theta. So this is r squared cosine squared theta, which is x squared, and y minus r squared sine squared theta, which is y squared. And that's the solution to the problem. This satisfies Laplace's equation in the bulk, in the interior of the domain, which is the unit disk, and satisfies the boundary condition. Now, when it's in Cartesian form, it's particularly easy to see the first statement, that it satisfies that the Laplacian equals 0. Evaluate its Laplacian in polar coordinate, in Cartesian coordinates. Second derivative with respect to x, 2, minus second derivative with respect to y, plus second derivative with respect to y, minus 2. So 0, clearly a harmonic function. But for this one, you'll have to do some trig to make sure that it satisfies the boundary condition. And for this one, it's very easy to see that it satisfies the boundary condition. Just plug in r equals 1, and you get this. But you will have to apply this operator to make sure, and it will indeed work, that it satisfies as Laplace's equation.